You stop talking.
Yeah.
And then I.
Okay, it's already live, right?
Okay, yes, it's live. It's already live, right?
Yeah. Now I need to turn off my YouTube voice, otherwise I hear my voice second time. Okay. Okay. Hello, everyone. Welcome to this session of Eurographics 2020 for the State of the Art report. My name is Lei Yang, and I'm a senior GPU architect at NVIDIA. And I'm going to give a brief tutorial, about 30 minutes, on temporal antialiasing, which is a family of techniques that is very popular in today's render engines. Work that I co-authored with my co-workers Edward Liu and Marco Salvi, who are both research scientists at NVIDIA. And next, to ensure that we have the smooth presentation, I've pre-recorded the presentation. In the meantime, if you have any questions, please you can either type them in the YouTube channel, and I'll gather them and I'll try to answer them at the end of the talk, or we can just do the interactive Q&A at the end of the talk. Either way is fine. So now, Martin, could you start playing the video, please? Before getting started, I want to thank co-authors Edward Liu and Marco Salvi, who are my fellow research scientists at NVIDIA. The full text of this paper is available online if you search for the title. There are two parts in this tutorial. The first part is a quick summary of what temporal antialiasing is, how it works, and what are the main components. The second part is about existing problems, technical challenges, and future venues for improvements with temporal antialiasing. Those are also the two main themes of this survey paper. The technique we are talking about today has been around for about 10 years. During this period of time, it has become almost the de facto standard for antialiasing in today's high-end 3D real-time renderers and game engines. It is particularly suitable for deferred renderers, since the traditional hardware-accelerated multi-sample anti-aliasing technique isn't really compatible with a modern deferred pipeline. We call it TA today, but 10 years ago the name temporal anti-aliasing meant something else in the research community. It was synonymous to what we call motion blur today, because motion blur is primarily used to remove temporal aliasing, or what is better known as the wagon wheel effect. Today the meaning of this term has shifted, so we choose to follow this new convention. This is a single slide overview of the basic idea of TAA. In a render without anti-aliasing, we shade one sample per pixel, which gets us exposed to all sorts of aliasing artifacts like shimmering details, jagged and crawling edges, MOIRE pattern, and so on. The standard technique to fix this is called supersampling, where we shade multiple samples per pixel and compute a weighted average of them using a reconstruction kernel. This is effective, but it is often too expensive to use on a real-time renderer. TAA adds temporal amortization to this process by blending samples at different locations for multiple frames. We still shade a single sample per pixel, but as we gather more samples over time, the image quickly converges to supersampled results. Of course, in reality, it can't be as simple as that. We can only fully trust the sample from the current frame. The previous samples can become invalid when the objects in the scene either move, be occluded, or change lighting. Those are the most important problems we need to deal with in all TAA techniques. There were some important milestones in the development of TAA. Here I'm listing some most relevant works and the major techniques that they've contributed to. I'm not going to go through each item now, but this table can serve as a reference when someone wants to study or trace down a particular technique in TAA. The paper has a more complete reference and descriptions of all the topics listed here. After these slides, I won't be putting citations in the slides of each topic. Let's dive into some more details. Here's a block diagram of how most TAA techniques work. The blue blocks are the TAA components, and the green blocks are from the render engine. As you can see, TAA is a recursive process, which means that the output of previous frame feeds into the current frame. For simplicity, we call that history. The first step of TAA is to reproject the history frame into the current frame to compensate for any scene motion. The renderer applies per pixel motion vector between the two frames to this step. And then we either validate or rectify the history data using color samples from the current frame render. Finally, we produce the output by accumulating new color samples into history. This output is post-processed by the engine to produce the displayed image, and it also becomes the history input to the next frame. Now let's take a closer look at each step. In order to perform supersampling, we apply a jitter offset to each frame's viewport. This offset is added to the projection matrix before the frame is rendered, so all the pixels in the frame have the same offset. We generate the per frame jitter offset from a log discrepancy progressive sequence to make sure that it has good spatial distribution over time, and this property holds regardless of where we start from the sequence. Here I'm showing the first 5 samples from the Houghton sequence of base 2 and 3 in the X and Y dimensions. This is a pretty popular sequence used by many TAA implementations. Normally, we cannot afford to keep the samples from multiple previous frames due to storage and bandwidth limits. Instead, we store a single history color per pixel. The single color contains a weighted average of the previous samples associated with the pixel. When a new sample is generated, it is combined with the history color using this exponential filter. The filter has one parameter alpha, which controls the relative weighting between history color and the new sample. It is also a recursive filter, and if we unroll it, we find that it unrolls to a weighted sum of all previous samples, with smaller weights assigned to older samples. Here in this plot, I'm showing the unrolled weights assigned to older samples. Typically, TAA uses a relatively small alpha to get more even weights over the previous samples. In some cases, we want this property from exponential smoothing that it assigns lower weights to older samples. The older samples are more likely to become stale, so it makes sense to phase them out. However, we must understand that uneven weights assigned to different samples can reduce the effective sample counts of anti-aliasing, and I'm showing the effect on the right. For example, with the fixed alpha equals 0.1, after 5 frames, we are only getting a quality of supersampling with 2 samples, if uniform sampling weights were used. After 10 frames, we are getting the quality of 5 samples, and with infinite number of frames, we are getting the quality of 19 samples at most. If we want to make the samples from every frame count, we need to use a progressively decreasing alpha from the harmonic series. So we've seen how history can be blended with new samples in each frame. Before they can be reused, they must be reprojected and validated. Reprojection takes care of moving objects or moving camera. It is based on the per pixel motion vector generated by the engine. The motion vectors tell each pixel where it can fetch its matching point in the previous frame. They are either computed from camera matrices for static objects or generated by forward rendered process for animated objects. Since there is no one-to-one pixel mapping between neighboring frames, most pixels in the target frame need to reconstruct the color in the middle of a pixel grid. We usually use standard resampling algorithms, like bilinear or bicubic sampling filters, to reconstruct those pixel colors. In reality, the reprojected history color can either be stale or invalid. This can happen with disocclusion, where the pixel was occluded in the previous frame, or with shading changes, or with incorrect motion vector. So to avoid leaking incorrect color into the current frame, we need to either reject or rectify them. An obvious way to avoid reusing invalid or stale data is rejection. We can detect invalid history based on some heuristics, such as testing whether depth, surface normal, object and primitive ID, or color matches between the 2 frames. These metrics are not always reliable, but they can be good hints in many cases. Depending on how confident we think the history is wrong, we can then either reject or fade out the invalid color by setting alpha to 1 or something close to 1. In practice, history rejection can be either tricky to implement or not robust enough. A major advance in TAA in recent years is the introduction of history rectification approaches, which basically biases the history values to make them more consistent with the new color samples from the current frame. Then we can blindly blend them with the new samples without contaminating the new frame. One way to perform the rectification is to take the color distribution from the 3x3 neighborhood in each pixel, and then compute the convex hull in color domain, and then clip the history color against that convex hull. Note that the chart on the right only shows 2 out of 3 dimensions in the color space, but you get the idea. The clipped history color is now within the same gamut of the neighboring samples. A more popular and practical implementation of this technique uses an axis-aligned bounding box in color space instead of a convex hull. The clipping operation can also be simplified as clamping to the AABB. It's a lot cheaper to run, but it's also less accurate. So another way of doing this, called variance clipping, is to compute the mean and variance of the neighboring samples, and then build an AABB around the mean and scale it by the variance. In this way, we can avoid being affected by outlier sample colors, which could have given us ineffective oversized color bounding boxes. Now we've gone through all major steps in TAA. One popular recent trend is to use TAA for upsampling, The way to do it is to increase the history and output resolution, but still keep the input sample resolution. Because the input samples are distributed over time, if we carefully bin those samples to a finer pixel grid, we can get a higher resolution image. This is why it has an advantage over purely spatial upsampling techniques. We present a full formal formulation of the temporal upsampling technique in the survey. Here in this talk, I'll just give a high-level description of the process. The key technique of temporal upsampling is what we call scaling-aware sample accumulation. The first step is to simply upscale the current frame samples using spatial interpolation. We'll get a higher resolution image, but it is blurry. When we have no history data, this is what we get. The second step is to blend that result with history. The history is already in target resolution, so we cannot indiscriminately blend the blurry current frame samples into history, because that will quickly turn the history blurry as well. What we need is adaptive blending based on sample location. The dotted circles here represent the range around each sample where it is allowed to be blended into history. The larger output resolution, the smaller range each sample has, and so in each frame, we only update the orange pixels which are covered by one of the dotted circle ranges. This is how sample binning is done. In practice, the range can be a smooth filter kernel, so blending doesn't have to be a binary decision. But this is an implementation choice. One special temporal upsampling algorithm that is worth mentioning is checkerboard rendering. The name means that we alternate checkerboard sampling pattern between odd and even frames and use TAA to fill the holes. This gives us a fixed 2x upsampling rate. To get the sampling pattern rasterization, we need to use some special hardware features. And then all deferred shading and post-processing passes need to be aware of this pattern. So checkerboard rendering can be more complicated to implement than regular temporal upsampling. Now that we understand how TAA and temporal upsampling algorithms work, next let's look at an image comparison in this beautiful forest scene rendered by Unreal Engine 4. We'll zoom into these two highlighted regions. On the left, we have input samples with aliasing. In the middle, we have TAA output, and on the right, we have temporal upsampling result. Both types of output were generated from a sequence of input frames like the ones on the left. These output images are much cleaner than the input and are without any temporal artifacts. The upsampled results on the right have sharper edges and more details on the branches and the leaves in the tree than the middle ones, due to the higher resolution history and the adaptive accumulation algorithm. Now let's look at the challenges in today's TAA techniques. We have detailed discussions of these problems in the survey in order to get more involvement from the research community to solve all these problems together with the industry. The first problem is blurriness, which is one of the main criticisms that many game engines get after switching to TAA. There are two reasons that contribute to the blurry look. The first one is history resampling. Because there's motion between frames, the history gets reprojected and resampled in every frame, and the error of imperfect resampling gets accumulated. The image here shows an extreme case of resampling an image 100 times with bilinear. Typically, it won't look this bad in TAA, because exponential smoothing will keep updating the history with new samples. But this is as bad as it can get when we use a very small alpha. The quality improves with better and more expensive resampling filters. With an advanced filter like SAC-NIHAP, there's almost no loss in quality, but it is at the cost of some runtime performance. The second problem, which is often overlooked, is the information loss during history clipping or clamping. This is because we use the current frame colors in each pixel's neighborhood to rectify history samples. And due to the low sampling rate, the current frame colors may not be representative of the underlying features that is sampled. So this process can often incorrectly remove detailed features in history. Let's take a look at this example. We have this thin foreground bar on top of a blue background. In the first frame, there is no history to reuse, so the output is simply what we sampled. In the next frame, we sample at different locations, and this time none of the samples hit the foreground, so the color bounding box of the 3x3 neighborhood does not include the foreground color. After clamping, the history loses the foreground feature. In the next frame, the feature gets sampled again. The history doesn't have it, but we can blend the new color into history, which results in a yellowish tint in the middle row pixels of the output, which hopefully you can see. Unfortunately, in the fourth frame, the feature is missed again, so the yellow tint in the history is again clamped to blue. Overall, we don't see the yellow bar with a significant presence in the output. Here we are looking at this highly detailed forest scene again, first with clamping, and then with clamping turned off. The difference might not be visible over the web presentation. So here's a close-up view of a small region, and hopefully you can see, with clamping on, we are missing details like small branches and leaves. To compensate for this blurriness, many TA implementations add a post-sharpening pass to recover some sharpness, but it can't bring back the lost detailed features. The blurriness due to clamping is also more pronounced with temporal upsampling, because the input samples are much coarser and have much higher chance to miss small features. Again, the two images here are generated with the same input, one with clamping and one without. The damage that clamping causes to the left image is pretty clear. The second challenge of TAA is ghosting, which is again often caused by imperfect history clamping. This often shows up when the foreground object moves across a highly detailed background and leaves a trail. When the background contains high contrast details, it causes the color clamping bounding box to bloat and become ineffective in removing incorrect history. On the right, I'm showing a visualization of the size of the bounding box per pixel, and you can see they are mostly big due to the high contrast detail that exists almost everywhere. The third challenge is temporal instability in MOIRE. This occurs when frequency of a feature and the sampling frequency are correlated. And because we are jittering sample positions every frame, we get alternating values that causes visible flickering. This could have been fixed by TA with sample accumulation. But with history clamping, the history value is forced to be clamped to the distribution of the current frame samples, which is often biased. So clamping forces to expose these flickering results. Here I'm showing the artifact with 2x temporal upsampling and with clamping on. You can probably see a lot of shimmering and MOIRE pattern on the containers. This is the same input and technique, except that the history clamping is turned off. The artifact is almost gone because TA is effectively integrating samples now. The last challenge is undersampling artifact. It happens whenever there is a newly disoccluded region that don't have enough samples to produce a decent image. Those regions may either appear overly sharp and aliased, or just contain noises that aren't stable. There are many ways to soften that effect, ranging from simple spatial filtering to applying morphological anti-aliasing techniques. All of those have been implemented in games and engines. So these problems prevent us from getting higher quality images, and they are mostly due to handcrafted history rectification techniques not flexible enough. This is a big venue that future research and development can focus on, especially since this will benefit a lot of apps and games. One recent trend that is showing promise is to use machine learning trained neural network to replace handcrafted heuristics. NVIDIA released DLSS 2.0 earlier this year, which includes a highly efficient model trained from thousands of images. Through years of development, we now can achieve much higher quality image reconstruction than traditional temporal AA and temporal upsampling techniques. Here I'm showing a comparison of 1080p TAA, 540p to 1080p upsampled by DLSS 2.0, and the same resolution upsampled by Unreal Engine 4's TAU, which is a popular version of temporal upsampling. It is clear that by replacing the handcrafted techniques with a more effective model, the upsampled results contains much more detail than TAU and appears even sharper than native res TAA, which also suffers from the challenges that I described earlier. There's a public Unreal Engine 4 branch that has DLSS 2.0 integrated, which you can download and try if you're interested. To summarize, I've introduced the basic idea of TAA and the major challenges that we are facing today. Since this is supposed to be a high-level intro, I've omitted a lot of details and references, which you may find in our paper. There are also other related topics covered in our paper that I haven't had a chance to mention. Also, if you want to know more about DLSS 2.0, there's a GTC 2020 talk about it by Edward that you might want to check out. That's the end of this tutorial, and I'll be happy to answer any questions you might have, either online or offline.
Thank you very much, Lai, for this nice overview on temporal aliasing.
Thank you.
As far as I can see, so far we haven't received any questions. Maybe I can ask you one
Okay.
regarding the history rectification.
Sure.
So that is purely based on chromaticity, you mentioned.
Yes. Sorry, before that, I still hear my voice echoing in the... I've turned off the tube video already. Don't know if that's... is it coming from?
So regarding the history rectification and the chromaticity, have there been different approaches or experiments with different color spaces, or just based on chromaticity being the best suitable one?
I'm trying to unmute myself and hopefully you can... Trying to unmute myself and hopefully you can... Trying to unmute myself and hopefully you can... Trying to unmute myself and okay. Hopefully you can... Trying to unmute myself and now I hear my voice again, but it's now it's very dim. Hopefully you can... Trying to unmute myself and now hopefully you can... Trying to unmute myself and now should be okay. So yeah, that's a very good question. So for history rectification techniques like clamping or clipping, they can be performed in any color space, although YUV or color spaces like those,
YUV
they are bigger in the bigger. Mute my. Okay. Let me try that again. So let me try that again. Let me try that again. Color space. Okay, so let me try that again. So the question is, what color spaces should we use to in the color clipping and clamping or any rectification techniques? And I think you can use any color space, but the thing is that most people choose to use spaces like YCOCG or YUV because they usually in those color spaces the luma channel is more separated from the chroma channels, and that usually results in a tighter bounding box, which will make it become more efficient in clamping the history color. So, but it still isn't ideal. So this, as I said in the challenges part, color clamping sometimes is still problematic, especially when the neighborhood of any pixel is busy with a lot of details. Then you risk giving a very big bounding box in those areas, and that with a very big bounding box, any color from the previous frame can leak through, and that will cause a problem. Like the problem, basically the problems I explained in that part. And I think there is an online question.
Could you briefly explain how HDR color spaces affect TA?
Right. Yeah, it's also a complicated thing, and I explained that in the paper. We explained that paper in the section, but I'll briefly say something about it here. It's complicated because we want to do TA after HDR resolve, but the thing is that a lot of post-processing effects happens before HDR resolve, and those also need anti-aliased results, something like motion blur or depth of field. If you use the alias result on those techniques, then they will sometimes there are pixels that with very high energy will create a big ugly blob, become blurred in the result, and that can be filtered after TAA. So it's a dilemma. So basically, you want those techniques wants TAA, but TAA you want to do that in the post HDR tone mapped space, and so the current practical solution, which is a workaround, is that you do a fake tone map before any post processing. So basically, use a approximate reversible tone map operator, and you tone map the HDR color to a LDR color, and then you do the TAA, and after that you can reverse that tone mapping operator, so you get back your HDR, you get back your color in the HDR space again, and then you can do all sorts of post processing with an anti-aliased results. And after all that, you can then perform the real tone mapping operator on it. So this is still approximate, because the fake HDR tone mapper or the approximate one is really approximate. So it's a generic tone mapper. It doesn't take into account the exposure and everything you use in the real tone mapper. So it's sometimes it has problems, and it will reduce the effectiveness of TA. But this is mostly what people do today. Hopefully that answers your question.
There's another one. They can't hear me, by the way. There's another one from Johannes. The last one.
Okay, there's another one. The question is, will DRSS be the future reference post-processing anti-aliasing technology, and we won't need TAA anymore? Or is there some TAA development going on that could catch up in terms of quality with respect to DRSS? Yeah, that's a very good question. I believe today DRSS can be a replacement for TAA, because it does everything TAA is supposed to do, plus spatial temporal upsampling. But if you ask if there will be traditional TAA development that could catch up in terms of quality with respect to DRSS, I don't really know the answer. Maybe there is, maybe there isn't, but it will be a really good research venue for future development. And I think with or without DRSS, there's both pros and cons. I mean, with or without deep learning or a machine learning based approach, there are both pros and cons that you can think about, and sometimes this will be a good venue for future development or research. And there's another question coming up for the thin line. The question is for the thin line problem, which you showed. Have there been any attempts to keep a history of the clamp AABB and incorporate to get those together with the 3x3 samples from the current frame? I'm not exactly sure what this means, because the AABB is derived from the 3x3 samples from the current frame. So technically, they're not the same thing, but they're from the same source. I think. Oh, I think the question is really about should we keep a history of the AABB and use that history information to better do the clamping. If that's what you're asking, then right, yeah, probably, very likely. This will help. This will help the quality, because with the chain of history, you will probably know that things like sampling artifacts or anything like flickering artifacts, you can probably detect that better with a history of the AABB. And probably you don't even need an AABB. You can get a history of a color sample. And by that, you can analyze the frequency content and maybe discover that this is really something that is due to that we are sampling different locations in that area, and that causes aliasing. So it's so that's definitely useful information. But the problem is that you don't. On the other hand, you don't really want to store a lot of data per pixel in the history, because if you do that, then reprojecting them will be a lot of overhead in terms of and it will hurt runtime performance. So you ideally you would want to reduce the amount of information that is reprojected every frame.
So if you want, we can wait for a bit more for some questions, or you can conclude the session if you want.
Okay. Yeah, there's a question that there is in terms of whether there is any new information or any paper planned to be published by DLSS for DLSS 2.0. I don't think we have any plan to make further publications on this. It's currently still proprietary technology, but the talk by Edward Liu gives a lot of information already, and it's a starter if you want to understand understand it better, or do some related technology that continues this path. Yeah, okay. If there is not more questions, then thank you all for your attention and for joining the talk. And there is as I said, a lot of details are in the paper, and I also recommend that a lot of talks that I cited in the paper in the paper that is worth checking. They also give a different aspects of the TA techniques that we discuss here. So hopefully the trend of this TA technique is of development can continue, and we can come up with stronger and better anti-aliasing and upsampling techniques. Thank you very much.